All right. Hey, everyone. So today I'm going to cover the second section from the book, the 5.2, the first law of thermodynamics. I uploaded, I'm going to upload both this like filled out version and the blank version. So if you want to take your own notes that are a little neater than mine or whatever, that's fine. You can just, print off the not filled out one and go through it with me or whatever you want to do. So the first law of thermodynamics states that energy cannot be created or destroyed. So it's also known as, we learned it as the law of conservation of energy. Okay, I'm going to try to do the best I can with this and see if I might zoom in and just move the paper then, because having it all the way out is just kind of too far away, I think. Okay, so the law of conservation of energy, it can't be created or destroyed. It has to come from somewhere, it has to go to somewhere. So we had the law of conservation of mass, right? Matter can't be created or destroyed. Energy is the same concept in terms of what we're doing here. It has to come from somewhere, it has to go to somewhere, okay? So it says any energy transferred from a system must be transferred to the surroundings and vice versa. So in other words, if you have the system, then you've got surroundings. So take, for example, I used the example of a can of pop yesterday. If you have a cold can of pop, right, and you set it out. So if you're treating the can of pop like the system, and then the air around it like the surroundings, what this says is whatever energy the can of pop loses, the air has to gain, or vice versa. Whatever energy the air loses, the can of pop has to gain. Okay? So this has an equilibrium then, because what one thing loses, the other thing gains. If you take, that's what this equation comes in here. Essentially, if you take the energy of your system and you add the energy of your surroundings at the beginning, that is to equal the energy of your system plus the energy of your surroundings at the end. Okay, it doesn't mean they stay the same. If your system energy goes up, so if the energy of the system has gone up, then the surroundings would go down to kind of balance out. Okay. All right. Internal energy. So the total energy of a system is referred to as internal energy. Okay. It is the sum of all the kinetic and potential energies of all the components of a system. So you could write an equation. Sorry, it's a little messy here. Let me zoom in on that a little. So total energy of the system is equal to the kinetic energy plus the potential energy. Okay. All right. Absolute internal energy cannot be measured, only changes in. That we're not going to really worry about that. It's one of those things like Heisenberg's uncertainty principle. You can't both know the place and the location and the movement of a particle at the same time. We're not going to worry about that too much right now. Calculating change in internal energy, right here, they give us this equation, delta E. Remember, the delta is change in, so change in energy. The way you calculate is you take the final energy, you subtract the initial energy. Okay? So they give us an example here, and just so you know that my highlighting colors correspond. So I highlighted the final in green. So anything that I highlight in green down here is going to refer to where you would get the final energy from. I highlighted the initial in pink. So anything down here highlighted in pink is going to be where you get the initial from. Okay, so an example, a mixture of hydrogen gas and oxygen gas has a higher internal energy than water vapor. So going from hydrogen and oxygen to water vapor results in a negative change in internal energy, indicating that the system has lost energy to the surroundings. So basically what they're saying is the ending this, the water vapor has a lower total energy than these two combined separately. Okay, so what happens then, the change in energy is less than 0, which means it's negative. A negative change in energy means the system loses it to the surroundings. Now, as you see over here, hold on, let me move. I put all of this stuff that they're talking about in this section, they're referring to the change in energy about the system. Because you can also look at change in energy for the surroundings. So you have to be careful and really pay attention to what you're talking about. Are we talking about the system? Are we talking about the surroundings? Okay. So in this case, we're talking about the system. So if this was the system, going from this to this, it lost energy, so your change in energy is negative. That makes it exothermic. An exothermic reaction means it's giving off heat. Heat is leaving the system, okay? If you did it reverse, water has less internal energy, water vapor. I don't know why they didn't put gas there. There should be a gas there. Water vapor turning into hydrogen gas and oxygen gas. This has a higher internal energy, so it has to gain energy for that to occur from the surroundings. That makes it endothermic, energy is entering, which would make your change in energy from the reactants to the products, the change in energy would be positive. Okay. All right. So that's, in general, talking about changes in energy, like from a reaction, from like the reactants to the products, stuff like that. Okay. All right. Relating delta E, change in energy, to heat and work. Okay. So from the first law of thermodynamics, when a system undergoes a physical or chemical change, the change in the internal energy, delta E, is given by the heat added to or liberated from the system, plus the work done on or by the system. So basically your total energy, and this sort of almost goes back to the to this here. Energy total is kinetic and potential. Okay. The heat, okay, plus the work, the combining of the two is going to give you your total delta E. Okay. So Q, over here, I did it in this margin, sorry. This is for this equation, the delta E equals Q plus W. These are the, what the variables stand for. Delta E is change in energy, you already know. Q is going to represent heat, and lowercase w is representing work. Okay. All right. So when, okay, I don't totally like how they worded this, so I kind of added something here too as well. So heat added to the system, again, remember, this is all about the system. Heat added to the system, your Q will be positive. Just like if energy is added to the system, the delta E was positive. If heat is added, your Q will be positive. If heat is removed from the system, your Q will be negative. Okay. And then this is the same thing down here. So this is just, I made this make sense here. Then this, work done by the surrounding on the system, is positive. Work is positive. And then the reverse is also true. Work done by the system on the surroundings will be negative work for the system. In other words, if the system is doing work on the surroundings, then it's transferring energy out to the surroundings. If the surroundings are doing work on the system, then work is coming in and energy is coming in. Okay. All right, so that's how to know like when you're using this equation, how do we know if the Q is positive or negative, and how do we know if the W is positive or negative? By these rules here. Okay. All right. Endothermic and exothermic. I already mentioned these up here. We've learned about it in Chem 1 as well. Endothermic absorbs heat. Endo is entering. So an endothermic reaction feels cold. Now this is the part like where people sometimes get confused, because they're like, well, if the system is gaining energy, it should be heating up, right? And the answer is yes. But think about how that affects the surroundings. So like, take a can of soda, right, that you pull out of the refrigerator. If you hold it in your hand feels cold, right? Well, the reason your hand feels cold is because the can of pop is absorbing or pulling heat out of your hand. So the can of pop is actually is endothermic. It's absorbing or pulling energy into it, because the can of pop is heating up. Where's it getting the heat from? Well, it's getting the heat from your hand. So it feels cold because your hand is part of the surroundings. So your hands are losing energy. Okay. So an exothermic is the opposite. The system is giving off heat. So it feels hot because it's expending or kicking off heat. So you burn wood in a fireplace. That feels hot because the combustion process, turning from the compounds that are in the wood, when the combustion process is occurring, breaking that up and creating, carbon dioxide and water vapor and stuff like that, that's giving off heat. So heat is leaving the system, the wood, and it's exiting into the atmosphere around it, the air and, people if you're near it, stuff like that. Okay. So an endothermic reaction, like I had up above, in an endothermic reaction, your delta E is going to be positive. This is for the system again. We're talking about for the system. Okay. Delta E is positive. Exothermic, the delta E would be negative or less than 0 for the system. Okay. All right. Last thing. State functions. A state function is, I have no idea why it's called a state function. It's weird. A state function basically describes the difference between the initial state and the final state of a system. Okay. So basically, if something is a state function, if it does not matter how it gets from the beginning to the end. If something does matter how it gets from the beginning to the end, then it's not a state function. Okay? So it says, for example, the altitude difference between Denver and Chicago does not depend on whether you fly or drive. It just depends on the beginning and the ending. Only on the elevation of the two cities above sea level. So I don't know if people know displacement, like displacement versus distance. So displacement versus distance would be like if you're walking, okay, so you've got different city blocks, okay? And if you're walking from point A to point B, okay, from place, sorry, not in the screen there. If you're walking from point A to point B, okay, and you walk and you go out here and you walk down around this block and then you walk up this block and then realize you went too far, so you walk up this block to get to B, right? So distance, the distance traveled followed the path, right? Okay, now what if you, let's see, going from point A to point, okay, so from point A to point B, the displacement is a straight line, distance. So displacement would be the length between these. The distance traveled, I should say traveled, how's that? Oops. The distance traveled, the path, okay. So are those going to be the same amount, like length or distance? No. Obviously this is longer than that, okay. So here in this example that I'm showing you, the displacement would be a state function, would be a measurement that's a state function, okay? Because it doesn't matter how you got from point A to point B. All that matters is the actual like ending distance from A to B. The path traveled, the distance traveled, the path is not a state function, because that does matter how you got from point A to point B. Okay, hopefully that helps it make a little sense. So they talk about it in your thing here in terms of energy. So they give this example of a battery in a flashlight can be discharged or used up by producing heat and light. The same battery in a toy car is used to produce heat and work. The change in internal energy of the battery is the same in both cases. In other words, if you put a battery in a flashlight and you use it to make heat and light, and you use all the energy inside the battery, the change from the beginning, the amount of energy in the beginning to the amount of energy in the end, the delta E, okay, it's the same for both of them. It doesn't matter if you used it to make heat and light or if you did it to do heat and work. It doesn't matter. The delta E is the same. So that would be a state function. Okay. All right. So hopefully that helps out. If you guys have questions, let me know. I'm gonna put up a key for yesterday's homework on there, so you can kind of check through that, and you can work through this stuff. All right. Good luck.